equation for undergraduate students. Today's topic is first order differential equations and their geometric interpretation. This is second lecture in this series. In first lecture, we had learned the differential equations, their meaning and significance. In first lecture, we learned that the differential equation dy over dx is equal to ky has a solution y is equal to c times e to the power kx. This we had obtained by the relationship between the exponential function and its derivative. If you do remember, actually we first took the exponential function and then find out its relationship with its derivatives. Thus, we obtained a differential equation, and since this given function was satisfying this equation, so we said that this is solution of this differential equation. Actually, we had experimented with some other equations and some other functions as well, but in all those experimentation, what we have done, we had actually said that this given function and its derivatives are satisfying this particular equation. So, they are the solution of the differential equation. But this may not be possible in many scientific applications, that is in those equations which are arising out of many scientific applications, it is not that much easy to guess either from which function these equations have been arisen or to guess which function will satisfy the given equation. This says is that we require to build some tools to solve the differential equations. So, we would start our topic formally. First, we will look at ordinary differential equation, and the first topic we will cover first order ordinary differential equations. First, we would look on ordinary differential equation. The first topic would be first order ordinary differential equation. What is first order ordinary differential equation? A first order differential equation must contain the first derivative y dash of the unknown function y, and it may contain the unknown function y itself and some known functions of independent variable x. Thus, general form of a first order differential equation will be f of x y y dash is equal to 0. Here we do have that this is a function of first derivative y dash function y and it may contain some function of x. This is called implicit form. This kind of differential equations are say y dash plus x is equal to 0, y dash minus 2a is equal to 0, y dash square minus xy dash plus y is equal to 0. We see that in all these equations, we are having the first derivative, the unknown function. In this first equation, I do have the function x. In the second equation, I do not have any term of x. In the third equation, we do have x, y dash square and so on. So, these are implicit form. But in actual practice, when we are actually solving, we may require to write these equations in explicit form as y dash is equal to f of x comma y. This kind of equations are as y dash is equal to xy plus 2x, y dash is equal to 2y, y dash is equal to x minus y square. We see here that is we are explicitly writing that y dash, that is the first derivative, is a function of x and y. Now, before going for solving this, finding out the method to solve these equations, let us first try to learn something geometrically what these equations are saying, and from that geometrical interpretation can we get something about the solution of this differential equation. Let us look at, we do know from the calculus that the first derivative dy over dx is actually presenting the slope of the tangent line to the curve yx at the point xy in xy plane. That is what this equation y dash is equal to fxy is telling us. It is telling us about the slope of the curve y at the point xy. Let me explain it more clearly, that how this idea is giving anything about the solution of this equation. Suppose yx is the solution of differential equation y dash is equal to fxy, then what it says, that at point x naught y dash x naught will give me the slope of the tangent at the point x naught y naught. But for this we do not require to know the function y. What we do have is actually, we do have that y dash is equal to fxy. That says is at point x naught y naught, I can calculate y dash x naught from this as f of x naught y naught. That is, we are not finding out what is yx. This equation itself is telling us at the point x naught what is the slope at the point x naught y naught of this function. Can we use this information to know the behavior or the shape of the differential equation solution? Let us just try to see it with the help of some example. See, let us take the example dy over dx is equal to y. Why I had chosen this example? We are very much familiar with this example that we had already done in our first lecture, and we do know the solution of this example also. So, we would be able to more clearly understand the things. What this is telling us? This equation is actually telling us that dy over dx is equal to y. That means the slope of the tangent at any point is equal to its y coordinate. What does it mean? It says is that if I choose a point, say 2, 3, then slope is 3. If I choose a point, say 3, 6, then the slope is 6. Now, at different points, if I am knowing this slope, how this is going to help us to get any idea about the solution. So, the question is, does the slope of tangent line at different points help at all to get the behavior of the solution? And if yes, then how they are getting it up? The answer here is, for this question, of course, yes, they tell us about the solution. To answer it how? Let us just see something more. Let me draw these slopes at different points on, say, some xy plane. You see here, I have taken the same equation dy over dx is equal to y. So, we are having here is, say, suppose at the point 4 and point 2, the slope would be 0.2 because the y coordinate is 0.2. So, in this line you see is that all this y coordinate is 0.2. So, the slope is 0.2. So, if I take, say, the point 1 and 1, the slope should be 1. So, you see is that is the slope is 1. Similarly, if I see a point, say this is point 6 and minus 1. So, this slope should be minus 1. Now, if I see in totality this graph, what it is telling? It is giving us a sense of direction. You see, all these arrows are moving towards upwards, here the arrows are moving downwards. Why this downwards? Because we do know the second, this y coordinate here is negative, so it is downwards. Slope is negative. That says is that I do get an idea about the direction of the curves. Now, for finding out any particular solution, we have to have an initial value problem. That means, suppose I say that at point x is equal to 0, the solution has the value 1. That is, I am taking the initial condition y0 is equal to 1. What it says that I have to include this point in the solution. The solution should pass through this point. Let us see if I do have any solution. Is it passing through this point? We see is that is C. I can, because what I have done is that is I have just drawn the solution as it was going on this one. Now, if I change my initial condition, say suppose I say that at 0 the function is 1.4. Now, still my differential equation is same, that dy over dx is equal to y. So, this direction is not changing at all. This direction is same. The only thing is it's changing is that is now I should have a function which should include this point over there. That means I can draw another solution like this one. So, what it says is that this we are getting the solutions at different points. Now, this graph which we are having here, this is called the direction field or slope field, and this idea of getting a solution from this direction field is known as the qualitative analysis of differential equations or the method of direction field. Sometimes it is also referred as graphical method. So, what we had learned, that is we have not solved the differential equation. What we have done actually, we have find out the direction of the slope of the tangents at the points x0 and y0, and from there we try to find out or try to approximate the solution. So, let us learn something more about this method. So, we will name this method as method of direction field. This method was actually first developed by Euler in early, you could say, is 18th century. He discovered a way to draw a graphic of those models which we are modeling as the differential equations. He has modeled them as a graphic one, and then he tried to say is to build up or that showing that the behavior of all solutions to the given differential equation without actually solving them. So, to learn something more about that, we have to learn some concepts about this method. So, first we will learn some terms. So, first is that is in this one, this direction field which I was having, these small arrows which I was having is the tangent lines at those points. These are called linear elements. So, now formally what will define the linear element? Linear elements are short line segments are a part of the tangent line at the point of tangency, which show the slope of the tangent at that point, and the complete figure, that is all the tangent lines at different points, that is called the direction field. So, formally what will be the direction field? The plot of all linear elements over a rectangular grid in xy plane is called the direction field of or the slope field. This direction field, we are showing this direction in this, we are showing by the arrows. How these arrows are being made? We just see the differential equation, because that we are having y dash is equal to fxy, and if at any point xy we are having that the function is giving me positive value, that means the slope is increasing. So, we show upward direction, and if at any point this function fxy is giving us negative sign, that means the function is decreasing and we show the slope downwards. How we do get the solution from this direction field? We see is that we visualize this solution as soon as we get the complete direction field on the rectangular field with the linear elements on the grid point showing the direction and dense enough to cover most of the space of the grid. How we are visualizing it? It's making, that is, we are actually basing our visualization on some facts. What are, you see, that is, once this direction is known, we can visualize it, that is, it should, any curve, it should move from here to upwards. If it is this side, it should move the downwards. So this is based on some facts. Let me just explain those facts. The first fact is the linear elements are solution of y dash is equal to xy. Why? We said that y dash is actually the slope of the tangent at the point xy. That means fxy at the point x naught y naught is the tangent slope. So what we do get is that at point x naught y naught, the tangent line would be y minus y naught is equal to y dash x naught times x minus x naught. So at point x naught, actually it will touch the curve. So that is at point x naught y naught, the contact point, this linear element, that is the tangent, and the curve, they would be same. So it is a solution of this differential equation at the point x naught y naught. This is the first fact. The second fact, so from here actually what we are saying is that this at the point x naught y naught, this is approximating the solution, and this is also named as the Euler's approximation. Second fact, solutions of y dash is equal to fxy do not cross each other. What does it mean? Let us suppose that they are crossing. So suppose at point x naught there are two solutions, y1x and y2x, and they are crossing at point x naught. So what we will do is, then I would assume that at x naught, whatever the value of y1 x naught and y2 x naught, that I will consider as y naught, and I will now look at an initial value problem. The initial value problem, y dash is equal to fxy, y x naught is equal to y naught. We do know that the solution of initial value problems are unique. Thus, what it says is that y1x and y2x at x naught are same. So what we say, for all x in a small epsilon neighborhood of x naught, this y1x and y2x would match, because at x naught they are same. That is, at that point if they are same, an initial value problem has unique solution. So they must be equal in that small neighborhood. So if in that small neighborhood it is equal, like that we do say, that says is that the solutions, if there are two solutions, they should not cross at all there, that is, the crossing is not possible. From all this analysis, actually we had learned something more also. The first thing we had learned is that if the two solutions touch at any point, then they must be same. And from this analysis we had also learned, that is, when we have to find out solution by using this method, we have to draw the linear elements in such a manner that they should not touch each other. We want them to be dense enough in the given field, but we should construct in a manner such that they should not touch each other. They should be separated. The third fact which we would be using is, that is, a tangent to an h to h solution yx nearly matches to the nearby linear element. Why? Again you see that is how we had got this solution. The tangent to the solution yx has slope y dash, and the equation says that y dash is equal to fxy, and we have drawn it as equal to fxy at point xy. That says is that this nearby point near the point xy, this y dash and fxy will match. Thus, the tangent to the solution curve at point xy will match to nearby linear elements. That says is actually that is, if it is matching over there, with keeping these facts in mind, we are now ready to draw edge by, what we mean by edge by edge solution, we will just go point by point. So, we can draw small edge by edge solutions yx on this direction field, keeping into mind two facts. One, that the solutions do not cross, and second, that nearby tangent lines should match. Thus, we will get, see, we just want at this point, so this nearby tangent, this is matching here, it is the point of tangency, and we are saying is it is matching, and we have drawn like this one. Now, if I say is that is I want to draw at this point, so I would have the solution which would be moving from here, and it should not cross this first solution. That says is this line, these linear elements has to be drawn. Of course, it should be dense enough so that I could get one could get the idea of the direction, but they should not be in a dense in such a manner that they touch each other, or when we are drawing the solution should cross or solution should touch each other. So, this, now let us learn this method. This direction fields, or this graphical method, this direction field we can draw by hand, or nowadays actually the computer softwares are also available to draw these. But before the invent of the computers, as we know that this method is been invented in early 18th century, this has been done by hand only, and here we would learn this method to draw the direction field by hand only. This method, when we are drawing it by hand, is called isocline method. What is isoclines? Isoclines are the curves with equal inclination. That is, one isocline curve means here all the tangent points will have same slope. Now, we will learn again this method by the help of this our example, that dy over dx is equal to y, or we call it y dash is equal to y. So, let us start step by step. The first step would be choose a rectangular grid. So, suppose here I choose 11 cross 22 points, so that I feel is that it should be dense enough, but it will be dense enough if I choose the range also accordingly. So, we choose the range, say for x minus 1 to plus 1 and for y minus 2 to plus 2. So, we had chosen this range, that is for x minus 1 to plus 1, for y minus 2 to plus 2. Of course, I have not plotted here the grid points, that is I would choose all these points, this 0.2, 0.2, 0.4, 0.2 and so on, like that we would have. So, once I had chosen this range and grid, first thing we would draw isoclines. How do we draw the isoclines? First we find out what is the isocline. Isocline is fxy is equal to m. Why? Because we are having the equation that y dash is equal to fxy, and y dash is telling us the slope of the tangent. So, the tangent would be fxy is equal to m, or we do call it, that is in our example it would be y is equal to m, because fxy was y. We have to choose 22 m's, that is we will choose for different values of m, so that I could draw the many isoclines. So, we will choose from minus 2 to plus 2 with an increment of 0.2. So, isoclines are the lines y is equal to m with m ranging from minus 2 to plus 2 with an increment of 0.2. Let us see that is how we are going to draw it. See. We do have at point 2, we have to draw the line y is equal to 0.2. At point 4, we have to draw the line y is equal to 0.4 and so on at 0.6, 0.8 and so on. Similarly, on the negative side at y is equal to minus 0.2, at y is equal to minus 0.4 and so on and all those points. Thus, we had covered the isoclines, we had drawn the isocline. What should be the next step now? The step 2. On these isoclines, we have to draw the linear elements. I have to draw this linear element should be drawn on each isocline. So, on each isocline f x y is equal to m, I am just explaining here in method in general and showing with the help of our example also. We have to draw many linear elements of the slope m. So, this also has to be done on many points. So, again we will choose the grid points, that is 11 points on the x axis, because our isoclines are y is equal to m. So, we do just have to choose the grid points for x only, that we have chosen from minus 1 to plus 1 with increment as 0.2, which says is that we would get at least 11 points on each isocline. Now, you see that is how we are going to draw. Let us choose first this isocline y is equal to 0.2. That means, here the slope is 0.2. Now, the grid points would be 0.1, 0.8 like this one from minus to plus side. So, we will start the first point at minus 1 and 0.2, the slope should be 0.2, that is I have to draw a line, a small line having slope as 0.2. At point minus 8 and 0.2, again I have to draw a small line having the slope as 0.2. Actually, this is isocline, means is at all the points on this line I would be having the slope as 0.2. So, thus at all points I will draw small lines which has slope 0.2. Now, choose this line y is equal to 0.4. This is isocline with our slope as 0.4. So, at first point minus 1 and 0.4, the slope will draw a small line having the slope as 0.4. You see, is it little bit upwards to this one. At the second point, we do have it as 0.4 and so on all the points I will draw it as 0.4. Similarly, I would go for each of isocline on the positive side. You see is that is here the arrows are also drawn to the upwards, because these slopes are positive sides. So, we do have, and similarly we get in all the lines we will draw on similar manner, that is the slope is, you see is that is how we are getting is the slope is increasing towards like this one. At the last line I have got the slope should be the lines which has slope 2. Now, come to the negative side, y is equal to minus 0.2. Here the slope should be minus 0.2. That says is that is at this point minus 1 and minus 0.2, the slope should be minus 0.2. That is, it should be magnitude is 0.2, but the direction is negative. So, we see that is we have got direction negative. Similarly, the second point it should be again minus 0.2. So, it would be going downwards and so on all the points on this line, it should have the same magnitude, but direction as negative. Now, come to the y is equal to minus 0.4. Now, the magnitude should be 0.4 and the direction should be negative, and at the second point as such. So, in all the points over here. Now, similarly, we can draw on all the lines. You see here is that is they are now giving the direction towards downwards only. Once I had covered this drawing the linear elements, Now, what will be the next step? This step 3 is sketch the solution. For sketching the solution, we see that first thing we have to see the direction of the linear elements, and we have to find out approximate curves such that direction of linear element is the direction of tangent to the solution curves. So, let us see that is how we are going to do it over here. This is our direction field. You see here, if we see at this point, the direction of the tangent is this way. So, we would like to have a curve such that its tangent should also be in this manner. So, let us see that is how we are doing it. So, let me just try one or two solutions. So, we see is that is here we are getting it say from this point, or say it is from this point, or you say it is at from this point, or it is at from this point or this point. This is from this point or this point. So, you see is that is how we are getting these solutions at different points. We do get it, that is if I am having this point, at this point we do see, we do find out that the tangent should match over here. We see here the tangent should match at this point. So, this is approximate solution. We are getting an idea that is how this curve should be going. So, first we see the direction and then we try to draw solution, approximate solution such that they are going. Now, do you remember that is in first lecture we have plotted the exponential function, and there we, if you do remember, we had plotted like this one many exponential functions. So, this is actually you are getting is it is approximately equal to the exponential function. So, we do have that this solution, we do know that the differential equation, which equation we had started, dy over dx is equal to y, and we do know the solution of this equation was y is equal to c times e to the power x, and c we could find out if I choose any initial point. So, you see here for y dy over dx we have got many solution, that is general solution, we have got all kind of curves, and you see is that if you remember these are matching with the exponential curve in this small field. And if I have to choose any particular solution, we just choose at that particular point which value it is satisfying, and that would be the solution. So, this gives us how to find out the solution of a differential equation without solving it, just using the geometric meaning of differential equation, that is the first order derivative, and what the equation is saying about this first order derivative. Second example, using isocline method, construct a direction field of about 11 cross 11 grid points in the region x for 0 to 2 and y minus 1 to plus 1, and sketch the approximate solution for differential equation y dash is equal to x minus y. You see that differential equation here is written in explicit form, y dash is a function of x and y. We will solve this equation by isocline method. So, let us move to the solution. First step, first the range and grid. Range here we have been given that we have to take the range for x from 0 to 2 and for y minus 1 to plus 1, and the grid we have been given that we should have at least 11 cross 11 points. So, first we will try, that is what are the isoclines. We see the given equation is y dash is equal to x minus y. So, the isoclines would be f x y is equal to m. So, here f x y is x minus y, that is x minus y is equal to m, or we would write as y is equal to x minus m. So, that we do have that they are straight lines having slope 1 and the intercept as m, that is the, as we are varying my m, that is the slope of the tangent to the solution curve, we would have different lines with different intercepts, only the slope of this isocline would be same. That says is, let us just try how many isoclines we have to choose. We have to do a little bit experimentation to see, that is whatever the range is given to us, that is for x 0 to 2 and y is -1 to 2, we should choose all those m's such that we could cover the complete field. That says is, that is we would be choosing here, after little bit experimentation we find it out that we will choose m as -1 to 2 with the increment of 0.2. So, what will be our lines? Let us see, that is at -1 isocline will be x plus 1, at -0.8 isocline will be x plus 0.8 and so on. At 0 it would be y is equal to x. Then at 0.2 it should be y is equal to x minus 0.2, you see that is our isocline is x minus m. So, thus we would have at 1 as y is equal to x minus 1 and at 2 y is equal to x minus 2. So, we are having as approximately 15 lines which are we are having from -1 to -1 to +2, that is these are the my m's, and we are having these isoclines. Now, we will draw these isoclines on our this grid. See how we will do. We will do it. First we will draw the range, that is for x 0 to 2, y we have taken from -1 to +1. Then we will start drawing the isoclines. At we do have the first isocline was y is equal to x plus 1. So, we do have is that would be, you see at first one y is equal to x plus 1. Here I had just chosen, that is because it is going out of our range. So, I am just taking a very small line here. Then at 0.8 it would be y is equal to x minus 0.8 and at 0.6 and so on. So, we are having all these isoclines for m ranging from -1 to 2 in this same this -1 to 2, that you see is that is why I have chosen this, because it is now completing our complete range space, that is our complete range is being completed, that is why. So, this little bit experimentation, that is what would be covering our complete field, we could use this what m should be there. Then what we do have the next step? Next step is that draw many linear elements. So, we have to draw these linear elements as many as possible, so that our complete field is dense enough, and we should have at least 11 cross 11 grid points. That says is that is we have to choose grid points. So, what I have tried here is, again these things you can learn by experimentation itself. Here I am just showing this example so that you do learn, that is in the second example how the experimentation we are looking. What we are doing is, on each isocline I have taken the intersection points with the line y is equal to c for the range c is equal to c minus 1 to plus 1 with 0.2. You see why I have taken it. These were our isoclines. Now, how to choose those points? We want 11 cross 11 points. So, that says is that is here what I have done is, that is you see I have chosen the lines y is equal to c like this one, these lines, and I have taken all the points at 0.2 difference with the 0.2. That says is that is I would be able to get some points on the isoclines itself. If I had chosen first my grid and then isocline, it may happen that I may not be having this grid point on the isocline. So, it is better to choose grid points after I have drawn this isoclines. So, like this when we are doing is, you see is that is at least 11 cross 11 points I will be able to get in this grid. Now, what it says is that on these grid points, now we have to draw linear elements, that is on each isocline x is equal to y is equal to x minus m at grid points. Draw small linear elements of the slope m. How we are going to do it? again let us see that is how we are going to do. We have to do it by hand and we have to be very much accurate, because if we are not accurate we will not be able to get the accurate solution. So, you see we would start for the first isocline y is equal to x plus 1. What is the m here? You to remember our isocline is y is equal to x minus m. That means if y is equal to x plus 1, our m is minus 1. That is, here is this grid point. So, first let me just plot the grid points over here. So, I have taken the first we are plotting the grid points over here. You see that is all these grid points we are plotting over here on each isocline with the intersection y is equal to c. Now, on the first grid point, isocline is y is equal to x plus 1, means m is minus 1. So, I have to draw a linear element, that is a small line having slope minus 1. That says let us draw it. Since the slope is minus, so I should have the arrow to downwards. Now, at the point, this isocline is which one? This is y is equal to x plus 0.8. That says m is minus 0.8. That means I should have magnitude of the slope as 0.8 and direction downwards. See this one. So, on the both the points it should be the same. Now, this is isocline y is equal to x plus 0.6 and we do have 3 grid points here. So, on all these 3 grid points we will draw small lines, that is the linear elements with the slope as 0.6 and direction downwards. You see like this, and this way we would be going to do for all till here, and you see is that is what is happening. At 0 what we would have, that direction is not being important, it should be just like that. But you see is as we are reaching to x minus 0.2, that means my m is plus 0.2. So, the direction should be upwards. You see the direction has been changed. So, now let me first draw all these lines and then we will explain it little bit more. We do have it here. You see that what we are having is, this is direction is, slope is minus 1, here the slope is minus 0.8, so on till 0. At 0 what will be, that is this is the line y is equal to x. So, m is 0, m 0 means is that it is horizontal one. So, we do have that isocline should be parallel to the x axis, and this direction is just been given. It is not necessary that we should give the direction over here, because 0 does not have any direction, positive or negative. Then as we move, y is equal to x minus 0.2. Now, that says is my isocline was y is equal to x minus m, that means m is 0.2, that is the direction should be, the slope should be have magnitude 0.2 and direction upwards. You see all these points we do have direction upwards, and like that we are going. When we reach to the point that isocline y is equal to x minus 1, x minus 1, that says is that m is 1 and the line is y is equal to x minus 1. This line also has the slope as 1, while as I have to draw linear elements also having the slope 1. So, they are just parallel to that line, that is they are matching with this line. This has very important significance, you see over here. Then we are going upwards, that is y is equal to x minus 1.2. So, the slope should be minus 1 point plus 1.2. And we are having like this, we are just moving once like this, we had completed this direction field. Now, we had completed this direction field. What it says is that now what should be the next step? Next step is to visualize the solution. How we are going to visualize the solution? You see, we have got this direction field. Now, I had removed the isoclines so that we do not have any other idea of the direction. We just have here our this linear elements which give us idea about the direction field. So, now let us see is that is what we have to do. This third step is sketch a solution. for sketching a solution, the first thing is we have to find out the direction. That is how this field, what this is giving us about the curve. Let us see one by one step by step. First step is to see the direction of linear elements. Now I am again using this isocline so that I could explain little bit more. We see is that from here, first we see is that is the direction is downwards over here. Let us see is that is one by one step. First we are seeing is that the line y is equal to x minus 1, this line, you see this line, and from this line if we see is the direction is moving here upwards something, and then here also something downwards, then here it is downwards. So we just make this first line, as I said, is this line has special significance, you see, because it is matching with this one, that says is actually it says that this must be a solution to this differential equation. So we see from this line we are having this is moving upwards, then it is coming up downwards. That says the significant lines are y is equal to x plus 1, y is equal to x. These are significant lines. So we do have is that is y is equal to x minus 1 to y is equal to x, the direction is upward. Then the next point, what we are observing, that from y is equal to x minus for y is equal to x to the y is equal to x plus 1, this is the downward, and actually at y is equal to x, as we said is that this is horizontal one. What it says is that the whatever be the curve, it is changing its direction at the point at the line y is equal to x, it is changing the direction at y is equal to x minus 1. Moreover, what we do have is that it is downwards from y is equal to x minus 1 to y is equal to x minus 2, all these things are downwards. So, let me summarize what we had observed from here. We had observed that, and again here I think is this one more point, that y is equal to x minus 1, we have the direction is matching with the that of isocline. Now, let me summarize the things which we had covered. We had seen that direction is upward on isoclines, y is equal to x minus 1 to y is equal to x, it is horizontal at y is equal to x, and it is downwards from y is equal to x minus 1 to y is equal to x minus 2. Here I think is I had left the point that y is equal to x to y is equal to x plus 1, it is again the downwards, and at y is equal to x minus 1, the direction is same as that of that isocline y is equal to x minus 1. So, first let us see this example that says is that same as y is equal to x minus 1. What it says? One thing it gives, that this should be a solution. Second is that since it is moving downwards from x minus 1 to x minus 2, that says is my solution should be moving downwards, that solution curve should be moving downwards from this line, and it is upwards from this line to this, that says the solution curve should be moving upwards. So, that those points again, that other solutions are curves moving upwards by the line, linear elements on both sides of the y is equal to x minus 1, that is upward downward like that we would be moving. Let us see that is how we are going to sketch it. Here I am just giving you the solutions, and then you see is that is how I had sketched it up. You have got enough idea that is how we are doing the things. First on the upside and then on the downside of the line y is equal to x minus 1. So, first thing what we had is actually that this line y is equal to x minus 1, this is one solution. Another is that the solutions are moving this way, because it is moving this way at the point y is equal to x, in this isocline you see is here it is little bit, what it says is horizontal one. That says is, of course, I think is I have not sketched any solution which is matching with any linear element on this line. What it says is that from here it is downwards, that says is the solution should, that is the curve is moving downwards, that is it is again going down from here, that this line is an important line from where the direction is changing to the downwards, while as here this direction is not changing in this field. We are getting is the direction should be like this one, that is at any point we are going up like this one. That says is, that is these are the solutions of this differential equation. So, what we have got, one particular solution we have got, y is equal to x minus 1, this is a solution. Then we are having these curves. What are these curves? Of course, we cannot identify the curves directly from these graphs, but we can check it whether this method is actually visualizing the solution or not, because this method says is that is just visualizing the solution, how the curves are, that how this function y would be moving. So, we just go by this one. So, let us just check it in the next one, that is what we can, how we can check whether we have visualized it correctly or not. So, let us see, that is analytical solution. Of course, we have not learned till now, that is how to find out the solution. Let us try again with the same method, that is first assuming some function and then trying to get, that is whether that function satisfies this equation, so that we could get an idea about the solution. So, let us write this differential equation as y dash plus y is equal to x. Now, first take this right hand side as 0, that is called actually homogeneous equation. So, first we will solve this homogeneous equation, y dash plus y is equal to 0. What we could write this, I think you do remember this equation, this is dy over dx is equal to minus y, and we do know the solution of this equation is e to the power minus x. So, the general solution would be c times e to the power minus x. Now, we have to actually find out the solution of this equation, not this equation. How we are going to do is, now we will assume one more function, let us say that ax plus b. If I assume this function, let us try to see whether this function satisfies this equation or not. For that, what we have to do? We have to find out its first derivative and then put this function and the derivative into the equation and try to find it out, so that I could get what are this, because I have taken here general form, I am not having any particular solution. So, here I am just giving you one way, that is we can use in general, that is ax plus b. Why I have chosen this? I can explain you. Since I do have on the right hand side x, that means whatever be the function of the solution, if I make it, I should get something x over there. Here we are having y dash and y. So, there must be some term of x, but in y dash that term should be disappearing. That is why we should choose, if it is right hand side is x, we choose it ax plus b. And now, our aim is to find out this a and b such that this function may satisfy this particular equation. Let us see it. So, this says y dash is equal to a. Now, if I am putting this on this given equation, what I would get? Y dash plus y, that means a plus ax plus b is equal to x. What does it implies? That a times x plus a plus b should be x. Now, equate the coefficients on both the sides. What it gives me? That a is equal to 1 and a plus b is equal to 0. Now, a plus b is equal to 0, what does it say? That b is equal to minus a, which is minus 1. That is what I have got, the particular solution, y is equal to x minus 1. Now, we can check, if I put what will be y dash will be simply 1. So, if I put y dash plus y, what I would get? 1 plus x minus 1, and the sum would be x. That means, this function is satisfying the differential equation. Now, what should be the general solution of this differential equation? Because this is one particular solution, here what I have got, and beforehand I have got that homogeneous system when I have taken that y dash is equal to minus y. I have got the solution y is equal to e to the power minus x. We will learn actually the method of solving these equations later on. Here I am just giving you one example just like that. So, what we do have is, that is, if we put this function, general solution, what we will be making, y is equal to c times e to the power minus x plus x minus 1. Now, we can experiment. If I find out what is y dash would be minus c times e to the power minus x plus 1. And if I put y dash plus y is equal to what it will be, I would be getting c times e to the power minus x plus x minus 1 and minus c times e to the power minus x plus 1, that will give me only x. That says is that this function is satisfying the given differential equation y dash plus y is equal to x. So, this is a solution, and if now you can use any plotter or you can just find it out, that is just like that we cannot handle, that is how this graph could be shown. We can just use any plotter and plot this function, and we will find it out that this would be looking like you just like these kind of functions. You would be getting for different values of c, you would be getting these different kind of plots. That what would be the solution. That says is that is by this we can visualize. So, this is not actually, this method is not giving us exact analytical solution. We are visualizing the solution at that some different points, that is we are just trying to get what would be at particular points. Rather you could say is that at any particular point I could get the value of the function from here. We can just make the value of the function at any particular point, I can just calculate the value of function. That says is that is discretely, or that we says is that is why we are calling it approximated solution. Let us summarize this method once again. First we have started with the, I am just summarizing with the help of second example. First we had the range, then on this range first we had drawn the isoclines. Isoclines we have chosen for different values of m we had chosen from minus 1 to plus 2 with the difference as 0.2. Then on these isoclines we made the grid points. How we had made the grid points? We took the intersection of the isoclines with the lines y is equal to c, and wherever they are intersecting, those points we have taken as the grid points. And what the range for c we have taken? We have taken for c minus 1 to plus 1 with again the difference as 0.2. Then on these grid points we have drawn the linear elements. Linear elements means that is on, we have to go isocline by isocline. So, on first isocline, because the slope is minus 1 and there is only one grid point which is being showing in this one. So, this graph, so we have done only one linear point showing the slope as minus 1, and second line slope is minus 0.8, and so on we have done till 0. At 0 the slope is horizontal, then we had gone to the positive side and the slope is on the upward manner. Like that we have done, and then what we have seen here, one more thing, that at y is equal to x plus 1 the direction of the isocline as well as that of the slope is matching. Then what we have done, we have seen the direction of this direction field. We have got, that is one thing we have got clear, that this is one solution, that is y is equal to x minus 1. Then we have got that my solution should move upwards from here, and so here this is moving, and whenever we are coming at 0, we see is that changing the direction, that means it should move downwards again, and from this side it is moving to this side like this one. So, thus we have drawn the solutions according to that, first on the upper side of the y is equal to x minus 1 and then on the lower side of y is equal to x minus 1. So, we have got what we have got. Of course, we cannot judge what is this function, but what we could do, we could find out at different points, we could find out the value of the solution at that point. If you remember our examples which we had in our first lecture, wherever these differential equations were appearing, we were interested to find out the solution at those points. Those points, that is, we are not interested very much what is actual function, we are interested only at certain points. So, this method actually gives me at those certain points I can find out, that is, what should be the solution. Here we conclude today's lecture. What we have learnt in today's lecture, that is understanding first order ordinary differential equations, their geometric interpretation, that is geometrically what they are saying according to the calculus, and we tried to learn something about the solution from that geometric interpretation. In that process, we learned a graphical method, or which is called a method of direction field or slope field, to find out the solution of first order ordinary differential equations without solving them analytically. We had also learned that this can give us the value of the function at a point, and we cannot approximate complete function or complete analytical function. That says is that we can solve some application problems without actually knowing that from which function these are generated, that is discretely we could find out the solution of those differential equations. To sum up this one, you can try this graphical method with the help of some exercises. So, here I am giving for your understanding some simple exercises which you can do. First is that y dash is equal to 2 plus 3y, another is y dash is equal to x plus y times 2 minus y, another is that y dash is equal to y minus sin x. In all these exercises, what you can do is, you just first think about what should be a proper range in which you could draw it properly, so that you can understand, that is the behavior of the solution. Then choose proper slopes for drawing isoclines. Try to see the isoclines, that is what kind of equations you are getting, whether they are simple lines or they are some curves. If they are curves, then you have to draw those curves. As in the third exercise, you are seeing that isocline would be y is equal to sin x, that is you have to draw the curve sin x. And what would be the isocline? Actually y is equal to sin x plus m, that kind of curve. So, you have to draw the curves like that one, and then on each isocline you have to draw the linear elements of that one. So, I think that you would be able to do it by yourself and learn the method more properly and understand it more clearly. That is all for today's lecture.